This video is going to look at the topics from the rest of Chapter 20 that we covered before classes were suspended. Let's first look at the effects of pH on dissociation. And so in this question, we're still going to be looking at acid-base equilibria, but now if I have the solution at a specific pH, I know a little bit more about my hydronium concentration than I do if I have not set a specific pH. With looking at these are going to be set up very similar to our weak acid, weak bases questions we've seen before. So I would first start by writing my equation, and then I would go through and make sure I've taken all the information from the question and put it into numbers that will help me when I do my ice table calculations. So the first thing I see is I have a pKa. Well, let's turn that pKa into a Ka so that I have something that I could set my table equal to. The next thing is I also see I have a pH, and so I can turn that pH into my hydronium concentration, which will help me in my ice table as well. The last thing I would do is before I jump to my table, notice that I have moles and a volume, meaning I need to convert those into molarity. And lastly, I would still write my equilibrium expression for everything that I see in my equation up top. Now we can go ahead and start our ice table. These are going to feel very similar. There's going to be one key difference. So I still know the molarity of my initial acid, and I know that at the initial point in time, I have a 0 molar concentration of my ions. However, since I know what the pH of this solution is, I know that my hydronium concentration has to be equal to the pH concentration. And so in this case, I do not know that A- is going to be the exact same thing because this is due to the solution pH, and my H3O plus from the acid is also taking part into that. So what I'm going to have to figure out in this question is looking at what is the concentration of A-. I can try to use the approximation here, but I can already say that if I look at these numbers, I'm going to solve for X and get a number that is about equal to 0.39 molar. X is not much smaller than 1, so I will not be able to approximate once I see my number. So I'm going to have to redo my table with the same numbers, but I'll have to keep X into each of my terms. When I go through this, I get an X value equal to about 0.28 molar, and the first thing I would do before continuing with the problem is to verify that that concentration is equal to my Ka, and those are close enough to my Ka. So I can say, don't forget for any of these questions that if I have acid, I must have hydroxide. And in addition, if this question was reversed, once you solve for hydroxide concentrations, you also have to solve for your hydronium concentration. So I would use the Kw relationship since the question states that I'm at 25 degrees Celsius. Since I know Kw is 1.00 times 10 to the minus 14th, I'm able to put in my hydronium that I solved for on the last slide and get my new concentration of all my species here. Notice the question said that it just wanted ions, so I would not need my HA number, but I included it here because we calculated every species present. The second part of this question changes pH. Pause the video now and try and do this one on your own. Okay, I hope you paused the video. I would start by doing the same setup here, writing my equation. I have the same pKa that I had from the first part. That hasn't changed. But since my pH has changed, I do have a new hydronium concentration. I still have the same molarity, and I still have the same equilibrium expression. My ice table is going to look very similar to the last question, except now, when I do that, I will now have a new concentration of my hydronium. Because my hydronium concentration has gone down, I know that my A- concentration had to go up, Le Chatelier's principle. So I know that X is actually going to be bigger than it was in the last question, and if the approximation didn't work last time, it's not going to work this time. So I can still go ahead using my Ka from the pKa, solving for X, distributing. Notice here, these numbers are going to be really close to each other. So we're actually going to see a really high concentration of A minus. And that makes sense because as we increase the pH, my hydronium concentration went down, meaning more of my acid was reacting in order to get to this pH. I need to check my concentration first, and if I have a value that's close enough to my Ka here, which it is, I can then go ahead and do the last part. I again have to solve for my hydroxide concentration, which I can use from the Kw. I put in my hydronium, and now I have my 3 ion concentrations as well as my acid if I wanted to include it here. Now, what about when my concentration of my acid equals my concentration of my conjugate base? Well, if we look at what happens with my Ka here, right? If my concentrations of A minus and HA are the same, they are going to cancel. And so at this point, my Ka is actually going to be equal to my hydronium concentration, which means my pKa is going to be equal to my pH. And so if we have an example here of acetic acid, we can look at this graph, which is similar to a titration curve. And we can see that at this specific point, this tells me what the pKa of the acid is. On this side, we see as pH goes down, I'm going to have increased amounts of my acid. And as pH goes up, I'm going to have increased amounts of my conjugate base. Why that's important is when we talk about indicators, indicators are weak acids and bases that undergo a color change using the same reaction we just talked about. Now, what I would say is I'm using a template here. There's no specific indicator called HIN. But what I want to make sure is clear before we go on to the pictures is that we're going to start using the terms protonated form and deprotonated form, basically meaning is the hydrogen of that species attached or not. And so what weak acids and bases do as far as indicators go is we're looking at going from the protonated to deprotonated form or vice versa. And we can actually monitor when that point occurs based on a color change. What would a question involving indicators look like? So in this question, it's giving me a pKa of an indicator and giving me information about whether or not the form is protonated or deprotonated, and it's asking me for the pH. So a couple things with these. You want to make sure you see that anytime we're given a pKa, we know that that's a Ka. We also know that there's an acid reaction happening here, so we can use our simple template. Remember, we're going to say that on the left-hand side is my protonated version, and on the right-hand side, I have my deprotonated version. And I can also turn my pKa into my Ka. And now, even though I don't have the numbers for what my concentration is of deprotonated versus protonated, I can use my equilibrium expression and rearrange it a little bit and say, well, if I have percents of both protonated and deprotonated, I can make a ratio on that side, and I know Ka is going to be a number that I just solved for, so I'll have only one unknown. So if I bring my pKa over and get my Ka, looking at this expression, while I don't have the numbers for deprotonated or protonated, I do know that I have a ratio of having twice as much deprotonated versus protonated. So I can use my percentages. The x's will cancel. I know that this number is going to be about 2. And then I can put in my Ka, solve for my hydronium concentration, and from there I can then use the negative log of that to get my pH of 9.501. It should make sense that this number is higher than the pKa because I see that I have more deprotonated than protonated in my mixture. The other type of question you'll deal with is when we're looking at solutions that contains more than one acid or more than one base. And so I have some guidelines on how you should set up these problems. The first thing you're going to do is write all your reactions in order of decreasing Ka or Kb, right? Because we're only going to be dealing with acids or bases. You're going to use ice tables to calculate the ions from the most important reaction. Then you'll do the exact same sequence for the second. And then the last part would be remembering our key ionization of water. And so as you go through these, make sure you know that if you're dealing with an acid or base, the acid's going to start generating hydronium concentration from step 2, and you'll need to use that concentration in step 3 and step 4. Let's take a look at an example. Find the concentration of all ions and the pH of an aqueous solution that has 0.35 molar diethylamine and 0.30 molar hydroxylamine. The first thing I would do with this question is to start looking at all the ions, and I know I'm looking for pH. So I would write my reactions. I know that these are bases because I see that they have KBs given to me, and I'm also seeing that they are nitrogen compounds. So I would write my standard base form for each of these compounds, pair it up with their KB. Remember, we still have my ionization of water that occurs as well. So my guidelines say that I should start with my highest KB value. And I'm going to use this and my concentration. I can go ahead and get started with my ice table. These questions are pretty straightforward. You're just going to be doing the same thing. They're a bit long, but it's nothing new that we haven't seen before. So I have my concentration of my initial base. I know that I have a concentration of 0. And I'm going to start to take away from the side that has my concentration and add to my side with 0. I see that my KB is 10 to the negative 4th. Let's go ahead and try to make our approximation here. As I look at my value for X, I get a value of 0.16, but when I put that back into my KB, I see that we're starting to get further away from what my KB is from the question. So I see that this is a little too high. This would be rounding up to almost 8. And so I'm going to need to include X here. In this case, I see that there's an X squared term, so I know the quadratic is going to be used. So if I recreate my equilibrium expression, keeping my X term in the denominator, I'll still have it being equal to the same KB. Remember, in order to get this solvable, we're going to need to cross multiply and then eventually turn my equation into having all the terms on one side. At this point, we can put them into the quadratic formula. My two roots are 0.015 and negative 0.16. I know that my negative one's not going to work here, and so I have two new concentrations for both of my ions that are products. Even though I just did the next thing would be to use these values and check KB, so I can put in my concentrations into my KB. I have one here, still not as close as I'd like. Some sig fig rounding issues probably are why these numbers seem so close to my original answer, but this is closer to my KB value in the question, so I'm going to go ahead and use it. The part that's different after you do step 1, remember that these are base reactions that are competing with each other. So before I can think about how much the base in the second reaction is dissociating, I know that this hydroxide we've calculated is going to be important because it's already in solution. So I can write my reaction out for the second reaction. I have my KB from the question. I can go ahead and start to do my ice table. I see that my KB here is much, much smaller, and so I feel way more confident my approximation would work, right? We're dealing with 10 to the negative 9th. So I can go ahead and leave out the addition and subtraction terms. When I solve this for X, I get 1.8 times 10 to the negative 7th molar. I can go ahead and check this, and I get a KB that's very close enough that I can go ahead and the approximation will work here. That means that I now have my X concentration for my conjugate acid. I can also add back my X into my equilibrium expression for my hydroxide, but this number is so small that it'll essentially still be my original hydroxide from my first reaction, and that's why that amount of hydroxide is so important. At this point, I can't forget about the autoionization of water, and so I still have a third reaction to do. I can write my reaction. I know what Kw is. My ice table will be much more straightforward this time because I know that I have an initial hydroxide concentration and I know that some of it has to create my hydronium concentration. And so I can use my Kw to get my hydroxide concentration. I would also need to show that I could add this to my hydroxide even though it's not going to change my number. But since the question asks for pH anyway, I'm going to need to calculate that number and then take the negative log of this. At this point, I should check. We just did 2 Kb reactions, and so I should see a basic pH, meaning something above 7 for this question. This is another example of a similar type problem. Notice the key difference here is we're dealing with acids instead of bases. Go ahead and pause the video now and try to do this one on your own. Okay, so what I would do would be to look again at what the question's asking for here. I'm just asked for my ions. I'm not asked for a pH. I would go ahead and write my chemical reactions out for nitrous acid and hypochlorous acid with, in addition, the autoionization of water that I would have at 25 degrees. My guidelines say I need to do with my highest Ka, so I'll be starting my ice table with this. Okay, so I can start with my first reaction. I have its Ka. Let me go ahead and put in my concentration. I know that I'm going to be solving for the concentrations of my conjugate base and my hydronium ion. I have a Ka that's 10 to the negative 4, so let's try to approximate. When I do that, I get an X value of 0.010 molar, and when I use that value to recalculate Ka to make sure my approximation works, I get a Ka of 7.1 times 10 to the negative 4th, which means my concentrations are close enough to my Ka, and I have concentrations for both my NO2 minus and my H3O plus. In the last example, we were doing bases. This example is acids, and so this first reaction, the hydronium concentration that I solved for, this is what I then need to use for my later reactions. So I can go ahead and repeat the process for step 2. I'll write my reaction out. I have my Ka. I can go ahead and put my concentration of my acid from the question. Remember, this is where we would need to use the concentration of hydronium that we saw for reaction 1. I'm going to then subtract from my acid and increase my conjugate base. I can look at my Ka. My Ka is 10 to the negative 8, so I can go ahead and try the approximation here. When I do that, I get a value of 7.3 times 10 to the negative 7th molar. Before we keep going, let's check to make sure that that would work and get us a close enough Ka. It does, so I know that this X value is all right to use. I would then take my X value, add it to my hydronium concentration. It's also the concentration of my conjugate base. And at this point, I would have the third reaction. The last part would be accounting for the autoionization of water, where I have my Kw. I can go ahead and put in my hydronium concentration that I solved for in part 1. Go ahead and complete this math. I know that my Kw is very small, and so I can use the approximation. When I do that, I will get my hydroxide concentration. I could also make sure that this number is added to my original hydronium concentration, and so here I can see that it doesn't change, but I would want to account for that. The next type of question is going to be looking at salt solutions. And so if you have the counter ion of a strong base, what I mean by that is really those group 1 and some of those group 2 metals that we associated with our strong bases. If you compare that or combine that with a conjugate base of a strong acid, the solution will be neutral. If you have the counter ion of a strong base with the conjugate base of a weak acid, that solution is going to be basic. And if you have the conjugate acid of a weak base, the conjugate base of a strong acid, that's going to be acidic. And the hard examples are if you have the conjugate acid of a weak base and the conjugate base of a weak acid, you're going to need to compare strengths. When Ka is greater, it's going to be acidic. When Kb is greater, it's going to be basic. And if they are exactly the same, they will cancel out and be neutral. Before we get into salts, let's just try to follow those rules looking at specific ions. So here I'm asking you to determine whether the given anion is basic or neutral. When I think about NO3-, I know that that's going to be a base. The nitrogen and the negative charge gives me a hint. So when I think about what that species will do after it's a base, it's going to be the conjugate base of a strong acid, HNO3. Therefore, this is going to be a neutral ion. When I change it to NO2-, I know that the conjugate acid of that is a weak acid, therefore it's going to be basic. So I'd encourage you to think about what is that ion going to do in solution. If NO2 is put in water, it's going to want to stay together as HNO2 because it's a weak acid. How does it get there? It's going to be from taking a H from the water, creating hydroxide. So here are 5 examples of predicting if a solution is acidic, basic, or neutral. Pause the video now and try to do these on your own. Okay, for the first one, I know that strontium is going to be a counter ion of a strong base, strontium hydroxide, which is going to make the pH neutral. My ClO4- is the conjugate base of a strong acid, which will also make the pH neutral, so this solution is neutral. NaCN, sodium again is a counter ion of a strong base. Cn- is the conjugate base of a weak acid, and so it's going to make the pH basic, meaning the solution will be basic. The next one has some unusual ions in it. What I'd recommend is look at the species we know are, and we see that is more common. So in this case, I know NO3 would be a common anion. That means that the rest of this is my cation. So what I have here is CH3NH3+. I know that this is a conjugate acid of a weak base, making the solution acidic. I also have my NO3-, which is the conjugate base of a strong acid, making it pH neutral, and so this solution is acidic. In the next example, I have lithium, which is the counter ion of a strong base, making it pH neutral. IO3- is the conjugate base of a weak acid, making the solution basic. And then the last example here, my ion is just sodium, and so I know the rest of that must be my anion. It's the counter ion of a strong base, makes it pH neutral. HCO3- is the conjugate base of a weak acid, making the solution basic. The other type of question you'll see with salts is looking at how we can change or calculate the pH of them. And so here in this case, I gave you the pH of an aqueous solution that's 0.123 molar, NH4Cl, and I told you that the ammonium has a Kb of 1.8 times 10 to the negative fifth. And I also know Kw. So for this question, I'm first going to need to figure out what is this salt. Is this solution going to be acidic or basic? I know that NH4+ is the conjugate acid of a weak base, making that part of the solution acidic. I know that Cl- is a conjugate base of a strong acid, making it neutral, which means this is going to be an acidic solution. The problem is that when I write the reaction out for my NH4, I see that I have a Kb. And since I do not have ammonia acting as a base here, I have NH4+ acting as an acid. I need to use my Kw relationship in order to turn my Kb into a Ka. Now I can go ahead and do an ice table like I would in all our other Kb questions. I have my reaction, I have my Ka, I can go ahead and put my concentration in. I see my Ka is 10 to the negative 10th. This is going to be a time where my approximation will work. I can go ahead and solve for my Ka. I get a value of 8.3 times 10 to the negative 6 molar. Let's go ahead and check that. I get a Ka that's essentially my Ka. So this number will work. I can go ahead and say, here's my concentration. That equals my hydronium. I can go ahead and take the negative log of that in order to get my pH of 5.08. I again can do a mental check here to make sure that my pH is below 7. It should be because I have an acidic solution. This next question is a very similar question. Pause the video and try this one on your own. Okay, I would start by looking at my compound, my salt, and seeing if this solution is acidic or basic. I know that lithium is the counterion of a strong base. I know that this species is going to be the conjugate base of a weak acid, making this solution basic. I would then go ahead and calculate, since I'm given the Ka of an acid, I would then need to be able to use Kw to get to a Kb. And before I could go to my ice table, I know that I would need to convert my grams into molarity, so I can use the molecular weight as well as the volume in liters to calculate molarity. So notice you can start these questions in a couple different ways, but really, how are you going to get the appropriate chemical equation with the Ka or Kb of the species from your salt, and then you need molarity in order to get to your table. So I have my reaction here. I know that it's going to create a hydroxide. I have my Kb. I can go ahead and put in my concentration. I know that we're going to be going towards the right here. I have a Kb that's very small, so let's try to use our approximation. And so here, if I solve for x, I will get a value of 5.2 times 10 to the negative 6th. When I use that to check my Kb, I get something 5.54, which rounding up would get me to my original Kb. So my x here is okay. I can go back. My x is my concentration of both the hydroxide and my conjugate acid. I can then use the POH, subtract it from 14 to get my pH of the solution. Since this is a basic salt, I should expect to see my pH above 7. And that's it for this video.